Today we are showing you the industry's first 16.3 gigabit per second backplane demonstration featuring the 20nm all-programmable Kintex UltraScale device. We're able to show you this demonstration just weeks after getting silicon into the factory. The demo consists of three elements: transmit performance, backplane simulation results, and receiver performance over that same backplane. This setup includes the UC1250 GTH characterization platform with the Kintex UltraScale KU040 device, driving one lane of PRBS15 into the Agilent DCA-X and another 3 lanes running PRBS31 through 30 inches of backplane. First, let's talk about transmit performance. Measuring the jitter of a transmitter eye is a great indicator of how well both the PLLs and the transmit circuitry are working. We're using one of the two LC tank PLLs available in this quad and are seeing 10 picoseconds of total jitter and 300 femtoseconds of random jitter. These are the kind of numbers that you would typically expect out of a 28 gig transceiver. We do have a touch of preemphasis dialed in here to help compensate for the losses through the board and this length of cable, but these numbers are really showing the performance of the GTH PLLs. Now, we have run a simulation in Agilent ADS using our IBIS AMI models of the GTH to show the impact of the full 30 inches of backplane on the signal. You can see that at the input to the receiver on the FPGA, the eye is completely closed. Yet we're able to recover the signal and have an eye at the CDR with some reasonable margin due to the equalization. This is possible because the IBIS AMI model is able to accurately reproduce the effects of our second generation auto-adapting AGC, CTLE, and 11-tap DFE, giving you an early look into how this transceiver will work in hardware, in this design or your own. And since it's hardware we're here to show you, we can reproduce those same simulation results using an IBERT bit file loaded into the FPGA with the Vivado serial I/O analyzer. Using the same 30-inch backplane we just modeled for, attribute settings sourced directly from the UltraScale transceiver wizard, and the same pre- and post-emphasis settings used to generate the eye on the scope, the receiver's auto-adapting equalization is giving us not only error-free link, but an incredible amount of margin. This eye validates the entire transceiver, from clocking and transmitter features through the receiver CDR and auto-adapting equalization circuits. It's important to note that the software tools used by our internal validation teams to do their testing and to generate this demo are the same tools we make available to our customers. The GTH transceiver wizard used to generate settings, the IBERT design configured into the FPGA, and the Vivado serial I/O analyzer to interface with that design. This ensures that all of the testing our engineers do in the lab translates directly into guaranteeing performance in your first UltraScale design. You've just seen a small glimpse of the performance that is already achievable with UltraScale devices via the 16.3 gigabit per second GTH transceiver, but there's much, much more to come. For more on the industry's first 20nm all-programmable UltraScale devices, stay tuned to Xilinx.com.